Dina, and welcome everyone to today's webinar, Reducing Legionella Risk in Your Buildings. I'm Ed Rutkowski, Editor-in-Chief of The Synergist, the magazine of the American Industrial Hygiene Association. I'd like to thank all of our listeners for attending today's event, and especially IDEX for sponsoring this webinar. IDEX Water is a global provider of water testing solutions that deliver easy, rapid, accurate, and cost-effective information on water quality to laboratories and public utilities around the world. We have two presenters today. Ray Petricic is the Director of Environmental Microbiology at HP Environmental Laboratory, and Dr. Dan Broder is the lead scientist for the IDEX Legiolert R&D team. I know we have a lot of information to cover in the next hour, so without further ado, I'm going to turn the controls over to Ray and Dan.
Thank you, Ed. As a brief intro, I'd like to just go over the agenda, which will be Legionella and the industrial hygienist. I'll deal with that. Then Dan will deal with the basics of Legionella. Then we'll talk about tools for reducing the risk of Legionella, which is the HOSIP or risk management plan. And then Dan will follow up with routine monitoring. At the end of that, we'll have 10 or 15 minutes for questions and answers. What is the hazard? This is an interesting question, and I think for industrial hygienists, it's one that is paramount in doing good quality work. And it centers around where the hazard might be found in the buildings that you might be testing. And I always find it that industrial hygienists should probably take a course in plumbing or minor plumbing before they do work in Legionella diagnoses. But that said, I think it's important to understand that in taking samples, it's important to know where to take the sample and how much sample, and do we take a fresh sample or do we take a flush sample? Do we use preservatives, and then what's the volume? And many of these questions can be answered with conversations with the laboratory of choice. And I think that it's important to form a union with the laboratory that you've selected that's going to be eventually doing the Legionella testing so that there's some continuity in both the collection and testing protocols. I recall just last year that we celebrated the 40th anniversary of the Legionella disease being discovered in Philadelphia at the Bellevue Stratford, where so many people died and hundreds were found ill. And the challenge for us today is to look at Legionella disease from a preventative mode. And I think that that mode is important to understand because I ask the question to myself many times after 40 years, why are we still dealing with Legionella in the same way? And the answer is we're not really winning the battle. It seems like Legionella is winning over us. So if you look at the CDC data in the last 10 years, you see that it's reported now over 200% increase. And so that certainly shows that there's a big concern for the health and well-being of people that occupy our buildings. It's also, and maybe this is the first take-home note, that there's been a paradigm shift from cooling towers to potable water. And this is specifically noted in hospitals and in large office buildings. And that should be an important issue when you go out and assess buildings. As an industrial hygienist, we all know how to anticipate and recognize and evaluate and control buildings. And this is all from experience doing lead and asbestos and eventual mold investigations, and now Legionella. So it's important that we know that the premise plumbing systems and have caused us a lot of problems with these associated outbreaks. And so we now have what I call kind of a Legionella risk anxiety, and many people have a difficulty trying to understand what that means. And so I like to look at it from the industrial hygiene perspective, looking at how they approach these diagnoses. And I look at it from the standpoint of building types, outbreaks or case investigations, assessments where you're doing water management, and specifically from validation testing where you're validating or clarifying routine testing. So it's important to understand, and maybe this is the second take-home notification today, is environmental monitoring is the key to prevention.
Okay, thanks, Ray. So I'm going to take over for a few slides and talk a little bit about the background of Legionella and the disease associated with it and some of the details about it. Just by virtue of the fact that you've tuned in today, I'm sure you probably have a pretty good idea of what Legionella is, but just for completeness, I'll go over just some short background of it. As Ray mentioned, this was discovered in the late 1970s when there was an outbreak at the Bellevue Stratford Hotel associated with one of the cooling towers, and about 221 people got sick and 34 people died, and they didn't immediately know why, but ultimately was traced back to this microorganism. And that was an American Legion convention, so they named it after that and called it Legionella. Legionella itself is not actually one organism, it's kind of a lot of different organisms, different species of this organism. The primary one is Legionella pneumophila. It's the one that's most common in the environment. It's the one that's nearly always associated with disease and I think pretty much always associated with outbreaks. But Legionella pneumophila itself can be subdivided into further categories called serogroups or serotypes, and there's about 15 of those. But far and away, the most pathogenic one is serotype number 1. That's the one that's nearly always associated with outbreaks, but they all have some level of pathogenicity. Then you have this other group of Legionella species that are not pneumophila Legionella, they're other species. And there's upwards of 50 of those, and I think the number gets a little bit higher every time I poke around. But these all have very rare associations with disease. Many of them have never been associated with disease, but some of them have on rare occasions. But really what you should be concerned about is Legionella pneumophila. This is the primary reason for testing and the reason for mitigating your any problems in your water system. So Legionella itself lives in a lot of different aquatic environments, but as it pertains to why you need to have a concern for Legionella in a water management plan is primarily because of biofilm. What is a biofilm? A biofilm is a stable structure that forms. It's a pretty simple sort of situation. Basically what you have is a swimming form of the organisms that's floating around in the water matrix. And this swimming form can bind to a surface. And when it does so, it can secrete various chemicals and molecules that form a stable structure. And this structure will stick to whatever it stuck to originally. And you can get an enrichment of the organisms in this structure. In some cases, you'll get multiple kinds of organisms, a whole community in there, some of which are biofilm-forming organisms, and some of which are just ones that have joined the biofilm that already was there. But in either case, you get an enrichment, and what ends up happening is these organisms can slough off from the biofilm and get back into the water matrix after they have multiplied. And in some cases, they'll come out of into your water, out of your tap. In some cases, they'll go to other places in your water system and set up a biofilm there. And you can see on the bottom here, this is just a hypothetical cross-section of this pipe where you can see that there has been buildup, which is a combination of bacteria and these secreted substances and possibly some sort of corrosive element that stems from the pipe itself. And on the bottom right, you can see a real cross-section of a pipe. This is sort of a worst-case scenario. You can imagine if this is a pipe in your building, you probably don't want the water that's coming through here, but this is a combination of all those things all put together. So Legionella can live in a lot of different kinds of water, but I think one type of water that hasn't really received as much notoriety in the news, though is accepted in the scientific community as really the biggest problem, is potable water. Potable water is just that, anything you can drink. So it can be showers, taps, sinks, faucets, drinking fountains. It can also be ice machines or even something a little bit more distant from that like a humidifier, are all roughly classified as potable water. You can get Legionella from these just as much as you can from other sources. What are the other sources? Well, the most famous thing is a cooling tower, of course. Cooling tower is shown in these central two images. On the top, you have sort of a zoom out of a common industrial cooling tower. And on the bottom central image is the fan that lives on the top of this cooling tower that really serves to cool off all the heated elements inside. There are other non-potable sources. There are many. Here's just a few of them. Decorative fountains can be non-potable sources of Legionella, baths or spas, misters in the supermarket, and even chillers. These are all sources of Legionella. Now, why are these particular kinds of water sources an issue? It all has to do with how Legionella infectivity functions. So here's a couple of pictures. On the left here, you see a shower head. And inside, in the zoom in, there's a little biofilm that's living in there, and you can see some free-floating organisms have come out. And basically the way this works is if you have a biofilm in there and some of the organisms are sloughing off, they can come out in your shower head or your tap. And in so doing, they may become aerosolized, and that's really the problem. It's the bacteria that are floating around in the aerosolized droplets. Similarly, if you look at a cooling tower, this is sort of a diagram of a cooling tower, and it's a pretty complex diagram, but the fact is really what you're looking at here is this fill material and the water that lives at the bottom. And what ends up happening in a cooling tower is this water comes through the fill material, and there's a fan at the top that's cooling it off. And as it cools it off, it goes down, goes back into the reservoir, which goes back into the building to cool off the heated building elements, and you get this cycle. But at the top, this fan is really serving to cool off the system. And if there is Legionella that has multiplied in either the fill material or the cold water at the bottom, what ends up happening is this fan will push this out into the environment. If there's a lot of Legionella in there, you're going to push a lot of this aerosolized Legionella out into the environment, which is probably why cooling towers are associated with most of the big outbreaks, is because you can push out a lot of material. Some of these cooling towers can be very, very large, and the fans can be massive and high-powered, so you can push out a lot of this aerosol into the environment. And it can go a pretty significant distance as well. So when there is aerosolized Legionella in the environment, it makes you infected by virtue of you breathing it in. Legionella is not something you get person to person, blood to blood. It's not transmitted from someone else. You get it from breathing in the water droplets. So you can imagine that because of that mechanism of infection, there are certain groups that are more at risk. Anybody that has some sort of compromised status with their lungs, if you're a smoker or you have a lung disease, you're immunocompromised or you're elderly, these are all groups of people or groups of individuals that are at higher risk for getting Legionellosis because of the mode of infection. This is one area of risk, the susceptibility of the patient. Also, as I mentioned before, the virulence of the strain. Not all the strains are created equal. If you have a particularly virulent version of serotype 1, that is another virulence factor. And then, of course, the extent of the exposure. How close were you to the source of where the aerosol came from? What is the concentration of the organism in that aerosol? That's a really big factor. And how fine were the water droplets? It tends to be that if the water droplets are smaller diameter, then you have a higher tendency to breathe them in, and that's a factor. So all of these are sort of risk factors, but the key here is that Legionella itself is not a terribly good pathogen. You kind of have to have all of these risk factors aligned together in order to become ill. Probably most of us have been exposed to Legionella at some point, but we've been healthy enough, or one of these factors really was not a strong factor, and so we didn't get ill. But if all three are in place, then you can get ill. The good news is that because it's not terribly good at what it does, it is controllable. You can control it, and that's really the key to this entire talk is how do you measure for Legionella, how do you control for it, and do what you're supposed to do. So should you be concerned with this? Well, as Ray mentioned, it's gone up. The number of Legionellosis cases has gone up. This is a snapshot that's taken right off the CDC website. It's from the Morbidity and Mortality Weekly Report, and you can see it's gone up almost 300% in the past 14 years as of 2014. Some of this is an increase in reporting, but not all of it. Some of it is truly an increase in incidence. 8,000 to 18,000 people a year get Legionellosis, and about 10% are fatal. There are some other places where you can get information about Legionellosis disease factors globally. One place I really like to go to is the European Center for Disease Protection and Control. They put out an annual report that gives you all sorts of details and parameters about disease incidence. And one interesting thing they have in their annual report is the seasonality of Legionellosis. You can see here, this bar chart changes from year to year, but not very much. It's pretty much the same in that you get this increased spike in the summer months. And I just can't help but think that with this kind of seasonality that's repeatedly produced each year, that with the increase of global warming and climate change, that this is going to affect this kind of plot, and that this bar chart's probably going to get a little bit taller and the shoulder's going to get a little bit broader each year. So this isn't going away. It's continuing to be a problem, even though, as Ray mentioned, it's been around for a long time. We're still having issues. This is a snapshot of some significant outbreaks that have happened in the last 16 years. I'm not going to go through all of these. I just want to pay your attention to a couple things. In particular, the ones in bold here are the outbreak at the cooling tower in Quebec City, where 180 people died, and 180 people came down with disease and 13 people died. Of course, in 2014, there was the Flint, Michigan situation with the lead in the water. That's still ongoing, but as of the time that this table was collected, 12 people had died after 91 had been infected. And then, of course, in the South Bronx, there was the cooling tower outbreak in 2015. This one was particularly interesting because this stimulated legislation. After this outbreak, there's new rules and regulations that now you have to test. You have to register all your cooling towers, and you got to test them on a quarterly basis. So this is the kind of thing that's significant. You're going to get more of these kinds of things happening when there are outbreaks and outbreaks that make the news. But one key thing about this is that there's a lot that are not cooling towers here. You see a lot of distribution systems. Those are basically potable. Some are unknown, but a lot of these are potable. Ice machines, building water system, and you see there are deaths associated with this, and cumulatively the number of deaths is actually more from this kind of thing. And if you look at the tally of that, the number of outbreaks associated with potable water seems to be more. In general, potable water is probably the bigger problem than cooling towers, and that's, I think, something that just a lot of people aren't aware of. So Legionella, I use the word ubiquitous here very loosely. It's obviously not ubiquitous, but it's very common in building water systems. One estimate has it's about 70% of building water systems have some level of Legionella, and it can be in utility and potable waters. And it's the building owners and managers that are the people that are responsible for controlling it. They are potentially liable. You can incur considerable financial penalties. Aside from the fact that there is a risk associated with the health, there's also a liability associated with that. But in general, Legionella is a growing health issue. It is preventable, and there's ways to prevent it. There's lots of really good ways to prevent it, and that's what we're going to talk about today. The CDC has estimated that about 90% of their investigations reveal that if you had just done some simple preventative care, you could have prevented the outbreak. What are the tools that are out there? There's some really good ones. Recently, ASHRAE came out with Standard 188. This has a water safety plan embedded in the document. It's the first standard in North America for its type. It's got a section in there that even tells you, it recommends how to do testing, who you should have do your testing. It's pretty thorough. If you read through it, it's pretty obvious on either A, how you should go about doing a water management plan, or who you should contract out to help you do a water management plan. Similarly, there is a CDC Toolkit. This is a very simple yes-no worksheet you can follow to help you examine risky building areas. It's got a walkthrough of a Legionella management program, and it gives you some scenarios, things that maybe somebody might encounter in their water management plan or something that they did not do properly and things like that. It's also got specific guidance for certain facilities. You can imagine if you have a population in your facility that's at higher risk, perhaps a nursing home or a hospital, you might want to put particular care to those places because they have a higher risk population than, say, like a gymnasium or something like that. So that's a really good segue for me to give it back to Ray, who has a lot of experience doing water management plans and risk management planning. So I'm going to hand it back to you, Ray.
Thanks, Dan. The importance here is also to understand from an IH standpoint that the CDC Toolkit and these other periodics are very important for you to be up to date on. And I'll just give you a list of a few things that are additional to the AIHA Legionella Building Water System Evaluation Control manual that was done by a group of very well-known experts. But things like the WHO 207, there was a Legionella and prevention of legionellosis. The Cooling Tower Institute has guidelines for best practices in control of Legionella. I think the U.S. Department of Labor has a technical manual that is pretty good. ASHRAE, obviously, their guidelines of 12-2000, and then the latest ones with the ASHRAE ANSI 188, I think is excellent for the industrial hygienists to become well aware of. And then, obviously, there's local guidelines of Pennsylvania, New York, Texas, Virginia, and others that will give you a lot of information about source identification, risk assessment, and control. So these are all important adjuncts to make you more aware of your investigation responsibilities. The other thing that is not really described in many of these manuals, but I think it's important for the IH to be aware of, is that you need to look at the buildings and classify them into three categories that I like: health care, which will be your hospitals and long-term care facilities and maybe your nursing and other types of facilities. Just general institutes such as hotels and casinos and maybe educational facilities, and an industrial, which would be like food and bottle, pharmaceutical, and manufacturing. It's important to look at that building type because each building type has particular elements that are a little bit different, and so the investigation has to be done appropriately based on that type. One of the water management and waste risk management plan questions that I always ask, and I try to document, are three questions that I always pose myself when I'm doing one, is that what's the hazard in that facility? What do you really identify as being the hazard? And how are you going to plan to control it? And then once you think you have it under control, how are you going to validate that it's continuing in the control? So there's a verification process. So as you go through a risk management plan and you look at these steps, it's important to apply control measures to the problem and reduce any significant hazards to any acceptable level that the industrial hygienist prescribes. So when you do these, you could be looking at chemical issues or biological, in this case Legionella, or you could be looking at physical properties. So be aware that some of these plans could be water risk plans and not just Legionellosis risk plans. So you really have to determine that up front as you're designing your program. In developing a risk plan at HP, one of the things that we do is obviously we mirror the 7-step HACCP, the Hazard Analysis Critical Control Point Protocol. And this was initially used by the ANSI protocol, where you conduct a hazard analysis and you determine the critical control points, or what we'll call CCPs, and you establish certain limits that you're going to accept. You monitor it by some schedule. You have a corrective action plan in place. You have a verification plan, and then you document. You document, document, document. So there's three aspects that I'd like to talk about briefly: the plan development, the implementation, and the program review. At HP, we provide a questionnaire or an inventory to our clients so that they can fill it out and inventory their equipment and have asked to them specific questions so that we can document in a flow diagram specifically the areas that we have of concern. And these are brought back to the team, which is generally associated members of that facilities group, which then will comment and design a plan for the client. The implementation is done many times where the facility people will do some of the monitoring. So it's important to know what they're presently doing and what kind of treatment might be going on, and if there's any testing, what that testing might show. So you're routinely dealing with the engineers of the building, and they're helping you understand their water system and in the development of this RMP plan. So the last step is a plan review, and this is something we've incorporated where we have a program we think is pretty comprehensive, but we feel that we have to come back every couple of years, and the reason for that is we want to test out the system to be sure that if anything's changed or there's been any cases of Legionellosis or any changes to facility or personnel, we can revise or update as needed. This is an example of a plan so you can see what it might look like. Typically for you, it might have a picture on it with an underliner of scope of services provided by your client of choice and risk characterization that we think are in that particular building at the point in time that we're evaluating. The most important thing is developing the team or members of that team, of which some are going to be part of that facility. It could be facility peoples and managers, but many times it's microbiologists, industrial hygienists, other consultants being brought in as building consultants to really assess and help assess the water system, whether it's utility or premise water. Then there's a descriptor under that which shows the building water systems, and what that does is kind of gives you a foray of what water systems we're dealing with, and everything from fire protection through point of entry or point of use. And so all that is very important so that one stop you can look at that front page and pretty much assess what's going on with a descriptor of the points of use, which is really important because many times the point of use in a core building of the tenant fit-up is totally different. So you have to know what's the building management's responsibility and what the tenant's responsibility, because many times you'll get into a core space and all of a sudden there's 300 hot water heaters and filters and so forth. Who's maintaining those? Who's responsible? So you better get that up front before you do anything else. This is a typical flow diagram that we will process with the client to kind of allow us to assess the risk. And the reason for that is because we want to determine what the control points or critical control points are within a facility. And by schematically looking at this in a very simple way, we can kind of describe the processes we may go through to help the client. And so there's really three essential functions that I look at when I see this. It's an identification of looking at the inventory flow of that facility and to assess the potential hazards, whether it's a CP or a critical control point. And then we set goals from this. We can actually process goal frequency, we can look at contingency plans, but we can set up verification and validation based on this. So this flow diagram becomes the meat and potatoes behind what we do. And lastly, we'll look at the process steps to validate the plan and make adjustments and then document it. Hazard analysis is an important aspect of this, and we use this process of the flow diagram and the walkthrough of the facility to really design the hazard analysis. And so what do I mean by that? What is the potential hazard for these processes? Well, I look at it basically in three different components, as I mentioned earlier: biological, and there's a subset of the biological, and I look at that from a proliferation standpoint and an aerosolization standpoint, because one or both can be very problematic, and so you need to be able to distinguish the two. Physical characteristics, that could be temperature checks and so forth, or chemical, looking at primary, secondary infection or disinfectants. I'd like to take a second just to identify the critical control point and CPs as part of the hazard analysis. Now, a control point is a hazard potential where the aerosol risk or the biological risk, or both, may be significant as a critical point, control point. So these are notable potentials that must be maintained and monitored, and implementing of some kind of a risk reduction strategy is generally advisable. The difference between that and a CCP, a critical control point, it's a hazard potential that presents a significant risk. And because of that significant risk, we generally give it a STEAM number or some kind of identifier because we know it's important. And the goal is to eliminate or reduce that hazard to some acceptable level. Defining monitoring and control limits for these CPs and CCPs is another important aspect. So control measures, what do I mean? Control measures are evidence-based industrial type practices that have been proven efficient to reduce the Legionella. And so we look at those control measures by monitoring tasks, and we monitor to verify that the control measures are actually working. And then we set up the frequency that we might want to monitor that, where it's daily, weekly, monthly, or yearly, that whatever's reasonable with that facility and whatever they might be doing should be taken into consideration. We set control limits, which are critical for each task that we're taking on. And then we have a contingency plan in case these critical limits are not effective, so we have some backdoor that we can actually control the situation. Environmental testing is, the way I look at environmental testing and sampling is extremely important for validation purposes. There's just no question. I think this example from AIHA work group is a perfect example of their thought, too, that validation is extremely efficacious, and it has to be done by Legionella testing, not by surrogate testing and so forth. I look at four things, and I call them the 4 A's. I call it access, act, analyze, and adjust. And I mean by that, I need to assess a development plan or risk plan. I need to act and implement that plan. That doesn't mean I stick it on the shelf and walk away. I hold team meetings and I analyze. Is it being verified? Are we validating it? Or are we having data that just looks a little bit skewed? And then I make adjustments at the end of the day. The plan is based on verification, validation. It's based on new scientific information that might come to the forefront. It may be based on new standards and guidelines. Whatever the reason, we have to be very proactive on doing something positive here. Lastly, the testing for Legionella, I think, is, again, another important statement by AIHA that the only way that we can protect the occupants of buildings, the only way is not a reactive way. You can't wait until you have people getting sick or dying. You have to test proactively. And that means a strategy, a plan that is solid, that doesn't sit on the shelf, that people know how to use and they feel comfortable with it, and it works for the facility. Dan?
All right, thanks, Ray. So as a nice segue to that, so Legionella testing is really my area in that I'm basically a test developer. But what I want to do is talk a little bit about when you do testing, what does it mean? And it depends who you ask. For example, this is a table that shows a lot of the different entities, both domestically and internationally, that have weighed in on what they think a reasonable amount of Legionella in your system is, depending upon the type of sample you're looking at. So, for example, the CDC and ASHRAE have some guidance, but the amount of Legionella in your system depends on the risk management plan, what is the type of facility, and things like that. AIHA and OSHA both have a fixed guidance of about 10 cell-forming units per milliliter, and cell-forming units basically is equated with viable cells, how many cells in a given unit volume. The VHA has guidance that says any positive. New York State Department of Health takes a slightly different approach, which is a really intelligent approach, which is to ask the question, do you have outlets in your building that have exceeded some level, but are greater than 30% of those outlets all exceeding that level? In other words, is your whole system at risk? Whether or not you find an outlet, for example, that has some excessive amount of Legionella in it, may not necessarily mean the whole system has a problem, but it could. Internationally, there are different limits. In France and Germany, here's a couple that basically say you don't want more than 1 CFU per milliliter. Now, this is for potable water. For non-potable water, like cooling towers, it's basically the same kind of thing, except everything's just 10-fold higher, which means that the expectation is that you may have a lot more microbiological growth in these systems, so you can tolerate a little bit more. But in general, the limits are all very similar, just 10-fold higher as that for potable water. So let's say you're doing your testing, and you have a reliable method, and you get some results, and it's higher than one of these numbers. What do you do? Well, you talk to your risk management professional, and he will tell you one of the following things. It depends on how much you have. If you have some low amount that's below this guidance or regulation limit, then generally what you'll do is continue with your water management plan and say, okay, it's working, keep doing what you're doing, good job. If you have exceeded one of these levels, say perhaps you're just above the limit, then probably you would increase whatever biocide you're using, maybe chlorine or something else. And then you would retest to make sure that what you did actually brought that level below the limit. If you are something higher than that, maybe 100-fold higher than the limit, you might take more dramatic action. You might superchlorinate or do something that's really going to try and remove the residual Legionella that are in your system. And then you would test again to make sure that what you did had the desired effect. If you have something higher than that, then you get into this sort of outbreak scenario where there's a very significant risk. And you might even shut the system down, or you might do some really, really dramatic sort of cleansing event or hyperchlorination or something else in order to remediate the system. Again, after that, you would retest to make sure that what you did had an effect. So there are regulations, there are guidance. Regulations are less common. They are on the rise, and that seems to be stimulated by the media and by the illnesses that result in some of the cases that are popular or that are focused on by the media. The guidance is more common, things like ASHRAE and OSHA, and it's well known that if you conform to the guidance, you're going to reduce the risk for illness. But when illness occurs, there's going to be a direct responsibility somewhere, and that brings me to liability. Who is to blame? Who's liable? In general, it's the owner or operator of the building. In some cases, it's the building engineers and the maintenance personnel, depending on the circumstances. I read recently about one case where there was a cruise line where some people got Legionnaires disease and died, and the cruise line itself sued the manufacturer of some of the sump pumps that went into the facility, and they won. So it can get pretty creative on deciding who's to blame for this, but in general, if someone gets sick, someone's going to look for someone to blame, and there's a lot of ammunition for doing so. And I just did a little exercise where I typed Legionella lawyer into Google and got a lot of hits. Pages and pages and pages of hits. And so I took about 6 pages worth of hits and I mapped out their locations to the United States. This is not a comprehensive list. I gave up after a while. But you can see there's quite a few. Many of these are law practices that focus specifically on Legionella. That's their business. Not all of them. Some of them have Legionella as part of their practice. But you can see there's quite a few. They tend to be congregated in the eastern half of the U.S. I wouldn't say that means that there's no Legionella lawyers in the central part of the United States. I just probably didn't get that far in my search. But they are all over the place, and there are costs associated with getting involved with these people. Here's a snapshot of some of the more significant settlements and awards in the last 10 years or so. This is just a snapshot. This is certainly not all of it. And these are just the awards. This does not account for the fact that if you do go to court, you'll probably have to pay a lot of legal fees. Even if you win, you probably have a significant cost associated with that. The best thing to do is to never have to go to court, to protect yourself by managing the risk diligently, and then hopefully, if you do everything correctly, then no one will get ill, and then you've protected yourself. Nothing's going to be 100%, but it's definitely going to be preventable. It's more preventable if you do something about it than if you don't. So, how do you reduce the risk? You test regularly to confirm what you're doing is working. You perform any correction actions you have to. You keep records of everything you do. You have records to show that you've done what you're supposed to do. That's defensible. It's good for the health of the people in the building, and it's good for you to protect yourself from a legal standpoint. So that's a nice transition for me to get into the testing part of this discussion, which is really what I do. I develop test methods, and I'll talk about one in a few slides. What I want to do is talk about what most people do right now. The gold standard is culture. What you're looking at here is a Petri plate on this black media called BCYE. And these are Legionella colonies on here. It looks like there may be more than one kind of Legionella. I don't know if you can spot them. But this is part of the problem, is that spotting Legionella is not trivial. You have to be pretty good at it. But what you do here is you're looking for this colony. You're going to count these up, and you're going to report back that number. The problem is that gold standard culture is not one method. It's actually sort of a blanket term that describes a lot of different methods that people do. People have the option to choose from a lot of different things. They can decide how they want to concentrate a sample, if they want to concentrate it. Legionella-containing water tends to have a lot of other bacteria in there that can prevent you from seeing Legionella on your plate. So you can do things to the sample to get rid of the background. Legionella has some pretty interesting resistances. It's resistant to low levels of acid and low levels of heat. You can take advantage of that to get rid of the background. So some people will do one or the other. Some people will do both. Some people will change the time of how long they do each. There's also different formulas of the medium. That black medium comes in a lot of different flavors. Each one is a mixture of different antibiotics that you can add to your plate. Each cocktail of antibiotics, it behaves differently. Some are very selective and will prevent growth of lots of stuff. Some are not as selective and won't. So people will do a variety of different things, and it's up to them what they want to do. Again, there's also confirmation methods. Now, when you look at one of these plates and you look at these colonies, you may be really good at doing Legionella testing, but you cannot definitively say, yes, this is Legionella. You have to do a subsequent test, a confirmatory test, which takes a couple of extra days if you do the plate media test, which basically means you take one of these colonies and you plate it out onto more media, some in which it can grow and some in which it cannot grow, and ask the question whether it passes that test. You can also do other molecular tests or microscopy tests or even sequencing if you want to get the full identity of the organism. In either case, if you have lots of different plates that come up, or maybe more than one colony on a single plate, you would confirm representatives of each colony type, figuring out which ones are real, and then go back and do the math and multiply by whatever you counted on the original plate. So there's a lot of subjectivity, there's a lot of variability, and there's some math involved. And we all like to think we're good at math, but the truth is that sometimes that's a problem. Different methods end up being different results. And this is really the crux here. This is just a snapshot of some diagrams we produced of the given standard methods. This is not all the standard methods globally, but it's some of them. On the top left is the ISO 11731 method, which has undergone some revisions recently, but this is a snapshot of it. The CDC method's on the top right. The AFNOR method that's used in France and in some regions of Canada is on the bottom left. These are all a little bit different in that they all use different numbers of plates for determining what the count is going to be. In general, Legionella is so hard to detect on these plates that you don't know what the bioload and background is going to be, that you're going to run a lot of conditions in parallel because you don't know which one is going to give you the final result. You got to kind of take a guess. So instead of guessing one, people will run them all in parallel. Most of the plates they'll throw in the trash because they're not usable. Some of them will probably have some count on them, and that's the one that they'll move forward with, do all their confirmations with, and get you a final result. But since everybody's not doing the same parallel plates, or even the same selective media, or even the same processes, you can get a lot of different results from this process. So it's pretty subjective, and there's a lot of variability. Because of this problem, people have tried to devise replacements for this. There's a lot of other tests that are out there trying to solve the problem of culture is so difficult. So at the top, culture, not fast. It's about 10 days all told. It takes 7 days for the original colonies to really come up to completion and then with confirmatory work, it takes a couple of extra days. It is quantitative. It's very labor intensive and subjective, and there's a lot of variability. Now, a lot of people have come out with so-called rapid tests. PCR is probably the most famous of that. It is a fast test. It's same day. It's kind of quantitative, but it reports out in genomic units, which are not viable cells. It's genomic units, which is based upon the DNA that's in their sample. But it's not equivalent to cell-forming units or to most probable number, which is, I'll talk about it in a second, which is basically the same as CFU. It does suffer some problems. It's got some cross-reaction if you have a complicated water matrix. When I say the matrix, I just mean the combination of the other bacteria and chemicals in the sample. That cross-reaction can impact how well the reaction is going to work. And it also can't resolve live versus dead. Since if you have a building that was contaminated with Legionella and you did what you're supposed to do and you treated it, that doesn't mean the DNA is going to go away. It just means the live cells are going to go away, so you still could get a reaction there. There's direct fluorescent antibody microscopy. It's also very fast. It's not really quantitative reproducibly. Also can't tell difference between live versus dead. There's a high degree of variability, and it does require concentration if you want to look at a larger volume. There's a lateral flow antibody test. This is kind of like the same concept as a pregnancy test. It's very fast, but it requires a lot of Legionella to get a result, so it's not super sensitive. It has a very limited range. It can really only look for Legionella pneumophila serotype 1, and therefore it's got a high false negativity. One other one, which is really interesting, is antibody capture. This is fast, it's a couple of hours. It is quantitative, though it actually does vary a lot. The problem with this is that it's very labor intensive. It's about 2 hours, but you're pretty much doing something for the entire 2 hours, which is not very practical from a routine monitoring water management plan standpoint. It's also expensive, and there's variability that's associated with difficulty of the method. So these are all touted as being fast, same-day tests, and that's really interesting. But the question you got to ask yourself is, do you really need a same-day test result? The answer is you don't for routine monitoring. These are part of a water management plan. If you take a look at some of the rules out there, for example, the rules that were instated in New York after the outbreak, they're having you test quarterly, every 3 months. If you're testing every 3 months, then it's pretty clear that you don't need to have a result the same day. You just need to make sure that your program is working. Take, for example, what happens at the New York State Department of Health. They investigate primarily outbreaks, And I think if you need to investigate an outbreak, having a same-day test is important because there's already a problem. Maybe it's made the news. You definitely want to stop that from getting more publicity. So you would do a PCR test to see if you have any positive. Then if you do, they're still going to do culture because they want to get a real quantification. You're not going to get a real quantification with the PCR, so you do the culture to follow up. The other nice thing about the culture is you get to take the bug home and stick it in your freezer. So if someone gets sick at the hospital and they happen to do culture on that person, which they should do more often, but they don't. But if they get a culture from that person and they isolate the causative agent, then they can match it up to what's in the freezer that you saved from your test. So it's a good epidemiological tool. You're not going to get that with some of these other fast methods. In New York State Department of Health, if they get a PCR negative, they'll just stop there and they won't move forward with culture. But this is a good example of where something that's same day is useful, but that's not for routine monitoring, that's for outbreaks. So this brings me to my next slide, which is, excuse me, Legiolert. Excuse me. Legiolert is a next-generation culture test. This is what we've developed at IDEX, and we think it's ideal for routine monitoring and for compliance. For the following reasons, it looks at Legionella pneumophila, but it looks at all serogroups. So it finds all of the critical causative agents of disease. It's very specific. There's little to no background interference, and I'll show you some data that backs that up. It's very, very easy. It's a simple color reaction, similar to our flagship product at IDEX. If you're familiar with Legiolert, you know how easy Legiolert is. And if you're not, I'll walk you through basically how it works. It's very reproducible. It's very repeatable, and we have protocols for all of the relevant water types for Legionella testing. It uses most probable number, which is basically the same as cell-forming units. There's no functional difference in those. And the test device itself can count up to over 2,000, which is much higher than a Petri plate. And it also doesn't suffer from the kind of problems that Petri plates suffer from. And I'll talk about that in just a second. It is not a same-day test. It's a 7-day test, but it is faster than standard culture because you don't have to do any confirmation work. When you get a positive result, it is a confirmed result. So looking at Legiolert itself, this is a device that we call a quanti-tray. Thank you. A quanti-tray is a device that holds the fluid and subdivides your liquid culture into a lot of different compartments, which we call wells. And this device has 6 very large wells and 90 small wells. And what you're looking for is whether or not these wells are going to change color. And this is a real sample right here. This is a snapshot of a true Legionella pneumophila containing water sample. And you can see here the wells that had Legionella in them grow up, and they turn over the indicator in the system, turns brown, and all you got to do is look for whether or not it's brown. So on the right is a negative control, and on the left is a positive tray. This works in conjunction with the blister pack reagent. This contains powder in it. You use the powder, and you use the tray together with your water sample, and that's how you get your quantification. So it's pretty simple to use. On the bottom is the potable water protocol. I'll talk about that first because it's the simpler one. Basically what you will do is you will take 90 mils of a sterile diluent like deionized water, and you'll crack open that blister pack and the powder pours right in there and you shake it up. And you add 10 mils of your water sample and mix it up so you have 100 mils of your final volume. And you'll drop that into this quanti-tray. And the quanti-tray is kind of like a bag as you get it. It's sealed on 3 sides. You pour the fluid in there and you send it through this device, which is a heat sealing device. And what it will do is compartmentalize that fluid into all the 96 different compartments. So what ends up happening is each one becomes its own little culture separate from all the other cultures. So each one is independent of all the other reactions. This is what's different than a Petri plate. A Petri plate has colonies that come up, but every colony is sitting right next to another colony. So if you have a colony that's not Legionella and it's secreting something that's inhibitory, that's going to affect the growth of its adjacent neighbors. That doesn't happen with this because every colony is totally independent. Every well is independent of all the other wells. So once you have this thing sealed, you drop it in the incubator. For the potable water test, it's 39 degrees. That temperature is important for the selectivity component of this test. It prevents background from coming up by growing at 39. There's a lot of bugs in the water that don't like growing at 39, and that's an advantage for detecting Legionella pneumophila. So you put it in there for a week, and when it comes out, this is what it looks like. It's very, very easy to read, and it's a confirmed result. When you're done, you see brown, you know you have Legionella pneumophila in there. The non-potable protocol is very similar with a couple of key differences. You're going to use a little bit less volume. non-potable water, you really don't need to test as much volume, and there's a lot higher background. So we only use 0.1 mils of the sample that ultimately makes its way into the final solution. But the way this works is you'll have 100 mils of sterile diluent into which you'd add your blister pack powder. And then separately, you'll do a short pretreatment by mixing an equivalent amount of your water sample with this pretreatment reagent that comes with the kit. You cook that for about a minute, and then drop in 0.2 milliliters of that. And since it's been diluted 1 to 2, 0.2 is effectively 0.1 of the original sample. Then the process is the same. You shake it up, pour it into the quantity tray, seal it, and put it in the incubator. For the non-potable test, it functions at 37 degrees. And the reason that's a little bit lower is you need a little bit more time to recover from the pretreatment process, and that gives you good quantification. So it's very, very simple. Does it work? Well, we did a couple different things to show that it does work. And one is something called a 13843, and this is basically a measure of the method against itself. So in other words, you're measuring a lot of parameters that are important to a laboratory. And I'm not going to go through the math behind all these. I'll just give you the qualitative of what these mean. Sensitivity is basically ask the question, of all the wells that were there that truly had Legionella in them, how many did you find? And the answer here was 98% in this study. Specificity is, of all the wells that were truly negative, how accurate was Legiolert? That was 99%. False positives of how many positive signals came up, how many were not correct, and that was 0.01%. And false negative is the opposite of that, which was 4.2%. Now, what's really interesting here is the last two parameters are repeatability and reproducibility. And this is a key part of Legiolert. It's very repeatable and very reproducible. And basically what this means is, with repeatability, if you have 100 quantity trays and they all have positives, that's going to take you a little while to read. But what you're asking is if the person reads 100 quantity trays and comes back 2 hours later and reads the same ones again, are they going to get the same results? And when we did this study, every user that did this had no deviations. Their results were exactly the same. I would definitely challenge you to do that with a Petri plate. There's no way you would get the same result if you did that. Reproducibility is similar, except now the user changes. So two different people read the same trays. Again, the same result across the board. So this speaks to how easy this method is to read and how easy it is to use. Another thing we did was a set of field trials. We really had a lot of success testing this internally, but then we wanted to understand if other people could do Legiolert as well. We did this with potable and non-potable water. The laboratories, we did them, and these are international trials, and we did this with a split sample analysis. So the labs would take their normal commercial samples, split them in two, and run one with Legiolert and one with their favorite method. We had them do confirmations right out of the tray. So they pulled the material out of these wells and asked the question, are these really Legionella when they're positive? You don't have to do that with Legiolert, but we asked them to do it just to show the specificity in these studies. We also segregated the data for pneumophila because the standard method does not have the capability of distinguishing between non-pneumophila species of Legionella and Legionella pneumophila. So we segregated it to do an apples-to-apples comparison. So I'm running a little short on time, so I'll just quickly run through the beta trial evaluation. And what I want to cue in here is on these graphs on the right. These are just X by Y plots where a given sample gets an X data point from the standard method quantification and a Y data point from the Legiolert quantification, and you get an XY coordinate from that. So if the methods both produce exactly the same and give you the same number, they should fall right on this 45-degree line. The fact was, when we did our potable water test against method SM9260J, which is the standard methods variant of Legionella test, we saw most of them, if you zoom in and look at the lower counts, were basically right on the line or above or below it within the noise. There were a few samples which were significantly above the line, and I think this kind of thing represents the problem with the standard. Occasionally it's going to miss, and in some cases it's going to miss with a very high quantification, which could conceivably be above one of those guidance limits. And if you look at the statistics, we do a couple different statistics. The more relevant one is something called the Wilcoxon test, because a t-test is good for data that's normal, that's all kind of in the same concentration range, but Legionella data can be really high and really low values, so it doesn't really work for a t-test. If you look at a Wilcoxon test, there does seem to be a significant difference showing higher sensitivity for Legiolert. There were no false positives recorded in this study. Looking at non-potable waters, we did 4 different labs, and this is interesting because there was no lab that did the same method as another lab, which is kind of part of the problem. everybody's doing something different. So we just decided we'll measure against whatever you got. And in general, non-potable tests for Legiolert performed about the same as all of the standard methods. We did one versus a strict CDC method. It's about the same across the board. One against SM9060J was the same across the board. You're looking at the zoom out and the zoom in from top to bottom here. Another lab did a custom method that's not like anything else. I sort of called it the CDC method, but that's not really what it was. And then the last lab also did a custom method. It looks like the last lab actually had slightly better sensitivity than Legiolert, although Legiolert didn't really fail to detect. It just had slightly lower sensitivity. And looking at the statistics, what you can see from the same statistics table here with the different columns representing the different laboratories, there's a real scarcity of green and red here, which basically means everybody was kind of the same. With this one laboratory as the outstanding outlier here that had slightly greater sensitivity. One interesting thing about here was the specificity. So in the other potable study, there was no false positives reported. In the non-potable study, there were some, but it was out of the 671 we tested, only 652 confirmed out as pneumophila. So that's well below the accepted level of 5% for a most probable number kind of method, which really leads us to be able to say that this is a confirmed result. When you look at these brown wells, Legionella pneumophila is in there because when you test all the ones that are positive, it always comes up as Legionella. So, my test results show that there's pneumophila in the water. Is this bad? The answer is not necessarily. There's other factors besides presence or absence. Of course, how much is there is important. Is this a change from a previous test cycle with your water management plan? Has something gone up? You need to have accurate tests to know this. And then, of course, are there lots of locations within your building that's positive? For example, the New York State Department of Health asks the question, is it a lot of your outlets? Is it 30%? So these are all factors in addition to whether or not you just find it. This is not just a presence-absence question. You're not going to eradicate Legionella. You might have some low level, and that's okay if you keep it low. So, our final thoughts here are that Legionnaires disease is preventable with a risk management or water management plan. The regulations and guidance and liability make it your responsibility to carry out that plan and make sure that it's working. In conjunction with that, we have Legiolert, which is accurate and consistent. It looks for pneumophila, which is the problem, the primary clinical and environmental disease agent. And this easy test means that more labs are going to be able to offer it. Industrial hygienists, premise owners can react with the best information to protect the public as soon as Legionella pneumophila is found. So I realize I raced through the data there at the end, but I'm happy to answer any questions as follow-ups to that. So once again, I want to thank Ray for joining me here today. And my name is Dan Broder at IDEX Laboratories. And with that, take any questions.
Okay, thanks, Dan and Ray. Been keeping track of the questions. We have several in only a few minutes here. Just wanted to let our attendees know that Dan and Ray have shared their email addresses in the chat box. So if you have any questions that I can't get to, please feel free to contact them after the presentation. First question is from Thomas, and he asks, is there a Legionella risk in emergency systems such as eye wash fountains and fire sprinkler systems?
There is a Legionella risk in eye wash stations. Any place where you have water that can be aerosolized, there's a risk. Ray could probably speak to more whether eye wash stations are commonly sampled or not.
They're not commonly sampled, but I think if your building starts to show some proclivity to have Legionella, it might be one of the points of use that you do check, but not as a routine. It's like point of entry. You seldom check the point of entry, but if your building starts having multiple issues, especially when you get 30% or more of the data showing some positivity at 1 CFU or greater, then it would certainly enhance further testing.
And sorry, the second was what? The fire protection areas? Like the sprinklers and stuff?
Very uncommon. Yes. Yeah, the fire protection is a very uncommon issue, closed loop, and seldom does that ever present a problem.
Okay. We'll see if we can squeeze in one more here from Bina. She writes that she's using the CDC Elite approved culture method for Legionella detection in cooling tower waters. If Legionella Pneumophila colonies are observed, the lab does a serotyping test to determine if it's serogroup 1. We start mitigation efforts when it's confirmed as SG1. Should mitigation efforts start when LP is detected irrespective of the serogroup or when LP SG1 is confirmed?
I think all of the serogroups have been found to be associated with disease. I think number 1 seems to be the one that's more commonly associated with the big outbreaks, but that doesn't mean the other ones are not pathogenic as well. I would treat them the same.
Yeah, I don't think you can discriminate there at all. And I know many facilities even start with people who have urine tests done where the SG1 is positive, even prior to the culture being defined.
Okay. And Bina had a follow-up question. IDEX Legiolert detects LP. Is a confirmatory method required to confirm serogroup, or can mitigation start upon getting LP positive results using Legiolert?
If you have a Legiolert positive, then you know you have Legionella pneumophila. It won't tell you what serogroup it is, but it'll tell you if you have pneumophila. So if you're concerned about pneumophila in general, which I think you should be regardless of the serogroup, then yes, you should start right away. But it's not going to tell you whether or not it's pneumophila 1 just by virtue of the fact that Legiolert itself is positive. It'll just tell you that it's pneumophila.
Okay. And I think we will get one more question in here before we're going to have to wrap it up. This is a question from Thomas. It says, testing for Legionella can be expensive. Is there a field protocol that can be used to identify Legionella or suspect Legionella?
You mean like something at the site of collecting the sample? No, I think that's a problem. The tests that I've seen and tried just do not give me reactions that can be confirmed later on. So I think you'd be best not to try fast and quick and do more definitive tests such as the Legiolert or culture.
Okay, great. Thanks, Dan and Ray, for your presentation. I think we're going to have to wrap it up now. We're a little past the top of the hour. I want to thank all of our attendees for joining us today, and especially thank IDEX for sponsoring today's webinar. Please join us on April 19th for our next Synergist webinar, the new TSCA and its implications. You can register for that at aiha.webvent.tv.